Good evening, all. I hope everyone can hear me properly. So, hope you all are having a good weekend, Saturday. So, right. So, having said so, basically, I'm from the tech team here in Skill-Lync, and then today we'll try to understand some of the engineering requirements for plastic design and development. Okay. So, I'll just share my screen. So, hope you all can see my screen now. So let's try to understand basic what are the topics which we are going to cover here. So I'll have a basic introduction about plastics. Plastic product design we'll cover. We'll try to understand what are the different types of plastics. We'll understand about different plastic manufacturing process, and we'll cater to the automotive industry, or we'll try to understand with respect to automotive industry how some of the manufacturing processes are important. So we'll try to dive deep into injection molding, correct? And then we'll try to understand some of the design parameters for plastics. What are the engineering features? What are some of the defects which you can come across whenever you're working with automotive plastics? We'll also try to understand in general what are the advantages and disadvantages uh, which we have with respect to plastics, and then we'll conclude accordingly, correct? So starting with plastics, hope you all must be knowing about plastics. It is basically a part of your life on a daily life. So plastics are materials which are made of polymers, or generally we call it as polymers as plastics. These are polymeric materials that can be molded into shape upon application of temperature and pressure. Okay, so plastics are basically moldable components, and hence the name plastic. Okay, deformable shapes, so hence the name plastics. Okay. So if you could see the screen, you can see basically in an automotive, these are some of the parts which are made out of plastics. We can see some of the dashboard components. We have the mirror cap. We have components which are in the exterior of the car made of plastics, as well as of the interior. Okay, so the bumper components which you see on the outside is generally made of plastics nowadays. There is reason behind why there is a recent uh, change in trend with respect to the number of plastic increase in the number of plastics used in automotive. We'll discuss that also moving forward, correct? So I hope this slide is able to give you an idea about few of the major plastic components which you can see in an automotive, correct? So having been said that, so how are plastics processed? Okay, so since we are trying to understand about engineering behind plastic design, we also should understand how plastics are being processed. So basically it's derived from natural or organic material. Okay, and generally the petroleum crude oil is one major area from which we actually derive or process plastic out of. Okay, so the distillation process we generally use for crude oil, and one of the byproduct is the plastic components. Okay, apart from petrol and petroleum products what we generally get. So plastics is basically an inorganic, general case, an inorganic material. Okay, so coming to engineering plastics, again the definitions almost goes the same, but there is improvement with respect to the properties, the strength factor, and then the chemical resistance accordingly. Okay, and heat resistance and other things. So we are basically trying to look into how the plastics has evolved over the years, so that different manufacturing process can be utilized for developing different plastics used in different sectors in the industry. Okay, we'll also try to understand what are some of the plastics used in automotive, and then what are some of those properties of those plastics used in the automotive as well, correct? So whenever you are looking into plastic product design, there are some of the things which we generally look into, or some of the parameters which we look into. Okay, so those are basically the functional requirements. Okay, so plastics are, or the components made out of plastics are supposed to do some particular function. So that will be one of the requirement which we'll be looking for whenever we are developing products using plastics. Okay, and then the reliability factor, how long it can last, and then how easily we can use it is one other factor which we are going to look into. And we are going to look into the manufacturing and assembly constraints, or how fast we can design and manufacture those components, and then the easiness with respect to we can assemble those components is some of the factors which we generally look into whenever we are developing plastic products, correct? So now coming into automotive industry, if you could see, we can see lots of vehicle in the market. Okay, and then we can see almost 50 percentage of the car structures are made out of plastics nowadays. Okay, so now there are reasons behind, as I was earlier telling with respect to the bumper example, there are reasons behind why we have a recent trend change with respect to increase in the number of plastic components, majorly because of the lower weight, but the higher strength capabilities of the material made out of plastics. And like metals, which gets corroded, we don't have that uh, uh, problem with respect to getting the part corroded easily. Okay, so there we have corrosion resistance. We can have better finish with respect to surface properties. Okay, we can have different types of finishes are made available. Okay, we can have hard plastics, soft plastics, we can have different textures, all those things which can be made available for the plastics, and hence it becomes a versatile material. Correct. We can have it produced in a cost effective way, and hence plastics find its use in the automotive industry. Plastics are also reusable compared to metal components. Okay, we can actually remold into different shapes so that it can be used again and again. Correct. So general classification is what we see here. Whenever you learn about plastics, we have thermosets and thermoplastics. So now let's try to understand what are the different factors with respect to how we classify plastics and thermoplastics as well as thermoset plastics. Okay, so with respect to shape, thermoplastics can be remolded, but thermosets, there is a factor which doesn't allows it to get remolded. It's basically the polymeric structure which is going to change accordingly in thermoplastic and thermosets, which actually have this factor added to the component. Okay. Now, with respect to strength components, thermosets are made out of hard plastics, and then thermoplastics are having comparatively lesser strength. Okay, and thermoplastics can be recycled very easily, but thermosets cannot be. Correct. And high melting point for thermosets plastics, as well as lower, comparatively lower melting points for thermoplastics. And thermoplastics can also be added with other additives so that we can actually increase the melting point and other things. So surface finish, when we look into thermoplastics, can have the very good surface finish, but thermosets plastics are generally very poor in the surface finish. Some of the examples which we generally look into thermoplastics are PET, polypropylene, polycarbonate, PC, PPA materials. Okay, and for thermosets we have vinyl ester, epoxy resin, bakelite, and other things. The bakelite, we generally see those are some of the hard plastics which we generally see in the industry, right? Now, if you see an automotive, it's around 1000 kg around a general sedan car. So out of that, around 162 kgs around 11 to 12 percentage of the total weight of the car looks into plastics of different types. Okay, in interior and exterior. So we have polycarbonate ABS material which are transparent. We have PVC, polyurethane, polypropylene, ABS material, EPDM, polyamides, polyethylene, polymethyl methacrylate, PPMA, okay, thermoplastic polyesters, and other materials. You can have a look onto it and understand what are the different plastics used in automotive, and then the in with respect to the ratio of the weight, how it is being distributed in a vehicle. Okay, so there are different types of plastics used accordingly based on the area of usage. If you see your lighting components, those are all transparent materials, and hence we find use of polycarbonate ABS materials. Correct. These are some of the examples of thermoplastics majorly. You have ABS, acrylonitrile, butadiene styrene, polycarbonate, polyethylene, polyethylene tetraphthalate, polytetrafluoroethylene, polyvinyl chloride, polymethacrylate, polypropylene, polystyrene, and so on. Okay. Similar way, there are multiple materials which you can find in thermosets, epoxides, phenol formaldehyde, polyurethane, and unsaturated polyester resins. Okay. So resins generally are classified into the thermosets category. So majorly when we are talking about engineered plastics, so we need to understand about the plastic processing or manufacturing process. So thermoplastics can be processed using multiple methods. It can be injection molded, it can be roto molded, vacuum forming, blow molding, extrusion, etc. Thermoset processing is generally based out of compression molding. Okay, since these are hard plastics, we use compression molding process for thermosets. So we'll try to understand what are some of the process used accordingly, and then we'll try to understand how it is being done. Okay, so starting with injection molding. Injection molding is a manufacturing process in which parts are made by injecting molten material into a mold. So you can see the image here on the left side, wherein the pellets or the granules of plastic is being actually pushed down a hopper, and then you can see a screw mechanism wherein it gets heated as well as ground, and then it becomes a molten stage when the heat is being provided. Now this molten material is actually pushed into a cavity, which is actually a combination of two parts close together to form a area which can be filled to form the plastic component. So we have the core and cavity arrangement here. So we'll have one part which is basically your core, and then the other part which is your cavity. So accordingly, you are going to have this mold created, and then the molten material will be injected to get your plastic component. Okay. So if you see components used in the automotive sector, your bumper components, your dashboard components, all those things, bigger components that you see are made out of injection molded or injection molding process. Okay, so it's a complex process as to see, but we'll also try to understand what are the stages involved. Okay, so here in injection molding there are multiple types which you can see. Okay, it can be vertical or horizontal types, okay, accordingly based on the position. Okay, so that's where you are going to understand how the different core and cavity arrangement is going to work. Okay, it's not just simply a core and cavity. We'll also try to understand what are the other parts. Okay, so basically you will be having other mechanisms like lifters, okay, side cores, etc., based on the complexity of your part. Okay, so accordingly we are going to work on injection molding. Okay, another process with respect to plastics are manufactured is auto molding. So one of the best example for auto molding is basically your water tanks. Okay, so here what happens is we have the plastic, powdered plastic, very fine plastic. Okay, so which will be put into a mold, basically two halves basically, and then the mold is heated, and then it is rotated to have a centrifugal action. Okay, so based on the centrifugal action, the powder actually melts, and then it takes the shape of the walls of your mold, and then you get the shape basically. Okay, so some of the water tanks generally are manufactured using rotational molding, okay, or roto molding we generally call, right? Now another process is basically the vacuum forming. So here basically we have the sheet of plastic material which are available, and then we have a mold which has vacuum holes where the air is being sucked for the plastic to take the shape. So basically the sheet of plastics is applied with heat so that it forms a semi molten stage, and then basically the vacuum created in the mold is able to make the plastic material take the shape of the particular mold. Okay, so this is basically a vacuum folding, vacuum forming process. Some of the plastic components used in automotive are also vacuum formed. Basically, components which you find on the interior of the door panels, some of the structures are basically vacuum formed. Okay, so blow molding is one good example with respect to blow molding is your water bottles. Okay, so these are actually created using blow molding process. Okay, so there will be plastic tubes which will be created, and these tubes will be actually put into a particular die shape, which is finally in the shape of your body. Okay, so now hot air will be passed into this particular tube structure, and then the hot air actually expands the plastic, and then finally takes shape of the particular mold what you're having. Okay, so this is how cans, your jerry cans for holding the petrol in vehicles, your water bottles, your inlet manifold components for intake of air, all those things in your automotive can be actually made out of blow molding technique. Correct. Now again, another process is extrusion, uh, basically. So what happens is basically, general case, if you could see here, pipes and all are actually extruded. Okay, so the plastic powder is being actually provided to a hopper kind of mechanism, and then heat is applied for it to be melted, and then it comes out of a particular steel die in the form of tubes. Okay, so this manufacturing process is called as extrusion. Okay, same process which you can see in sheet metal or metal processing also. So for plastics also we use extrusion process for creating pipe structures, right? It need not be circular structure. It can have varied variety of shapes as well. Cross sectional shapes can be varying as well, right? Now coming into compression molding. So here what you are going to have is a basically charge, generally called the particular plastic which we are having the solid form as a charge. So heat is applied to this charge in a mold basically, and then it takes the shape of the mold. Okay, it deforms and it takes the shape of the mold. The problem here with respect to this compression molded part is it's only one time use, or it can be only molded one time. Okay, hence thermoset plastics are usually used for this kind of compression molding operations, right? So basically looking into the injection molding process. So basically the first stage will be where we are feeding the material. Second stage will be the plasticization, where the melting of this plastic pellets happens. After that, we are actually going to do the injection, where it's being filled into the cavity area. To make sure that the filling is proper, we are going to have a pressure for holding it in, holding the shot in the core and cavity area or the cavity area. Now, there will be water lines available in the core and cavity for the cooling process. After the cooling is done, we open the mold, and then the mold is released by using ejector pins. Okay. We can have a look onto the different parts actually. So you can see a top clumping plate. Basically, a runner is the area through which the molten material is pushed or pressurized into the cavity area. You can see the core block as well as the cavity block, and the area in between is basically going to be a part. Okay, so the parting line is where you have the core and cavity being met. Okay, so we'll have to apply the pressure to hold this core and cavity together, and then the injection of the plastic component happens, correct? So we can see the ejector housing as well as the ejector plate. So as soon as the uh, plastic is cooled down, the cavity or the core moves away, and then we have the ejector pins to push the plastic out of this. Okay, so the cavity is going to be the stationary part. I mean, the cavity is going to be the stationary uh, component, and then the core is going to be the moving element here, right? So it's a two plate mold. Similar way, you have three plate mold basically whenever you're having additional runner plates to hold it in position, correct? So these are basically vertical injection molding machines, right? Now we'll try to look into some of the plastic design parameters which is really required for you to work around with plastics. Okay, so one major part is with respect to tooling axis. Okay, so whenever you're working with injection molding, tooling axis becomes a one important parameter. Okay, so this is the direction in which the core and the cavity moves, or the cavity is fixed in position and then the core actually moves. Okay, so basic requirement is for the core to move out so that we can actually eject the part from the component. Okay, so this is basically the direction in which the mold blocks actually move. Okay, so that's basically the tooling axis. This is very important with respect to from the designer's perspective whenever you are designing the component, because with respect to your tooling axis only we are going to check with respect to other parameters which are going to learn next. Okay, so the next parameter is going to be the draft angle. Okay, since we are dealing with injection molding. Okay, so along with the tooling direction we also need to have some draft available for your mold components. Okay, so whenever you are designing the part also, it is going to have an opening angle. Okay, so this is to make sure that the mold doesn't scrap the final product. Okay, so if it scraps the when it is a 90-degree, it scraps the metal, scraps with the plastic component, which can actually affect badly with respect to the plastic which we are going to manufacture. Okay, so this can lead to defects. Okay, so we need to avoid these defects, and hence we are going to provide some draft angles. Okay, there are some standard values with respect to draft angles which are going to provide, and then it ranges from 0.5 degree to 3 degree general. Okay, so 3 degrees the general criteria. We can come down up to 0.5 degree when we look into the engineering features also. Okay, we'll try to understand what are engineering features also moving forward, but general with respect to plastic components, we actually have a draft angle, and then the draft angle value is around 3 degree. Correct. Now you can see some of the components which are manufactured wrongly or incorrectly, and then what are the changes which you need to make according. Okay, so if you could see part with draft, you can see the minimum draft being 0.5. And you can see in the second image where it is perpendicular, okay, 90 degree to the main wall surface. We should have a angle of 0.5 degree accordingly. Okay, similar for engineering features, you can see something here is a screw boss kind of structure. For that also you should be having a draft available. Okay, so why this draft is available is basically to make sure that there is no wear and tear happening with respect to your mold components. There is no warpage with respect to your plastic components. And then with respect to your draft, it's going to make sure that the ejection happens easily, and then it's a smooth process, and then it involves in having a proper surface finish being developed. Okay. Now, increasing the tool life is also another factor which we need to look into with respect to developing your core and cavity blocks. These are metal parts which are manufactured, okay, for the injection molding process. So now, if the design of the plastic, whatever you designed, is improper, and then accordingly when you design your core blocks, that will also leads to the reduction in tool life because of the wear and tear happening to the parts. Okay, so draft angle is very important with respect to plastic development using injection molding. Okay, so these are some of the factors which you need to look into. As a design engineer, these are some of the standard values which you need to follow while you're actually going to design plastic components, right? Having been said that, we generally perform draft analysis. So draft analysis is performed on various stages of the design process for the plastic component as well as the mold part. Okay, so we'll try to look with respect to the plastic component as such here. So you can see a part as given below, and there is different surfaces available. Okay, and then you can see somewhat angles is being provided to surface. So this is a physical or a model for which a draft analysis is performed along the vertical direction or normal to the top surface here. Okay, then you can see all the surfaces are green, and then general criteria stating that all the surfaces should be in a particular color based on whatever we are providing. Okay, if we provide green is for green color, then it shows us that 3 degree condition what has to be met is already met here. Okay, so that's what we actually see here with respect to the green color. Okay, so this provides the information with respect to component moldability. We are trying to understand whether the given component along the given tooling direction can be prepared using injection molding process, and hence we are going to perform this draft analysis. Okay, any plastic design engineer, when they are provided with a surface for developing plastic component out of it, generally performs a draft analysis for the classes surface as well as finally after creating the plastic component. Okay, these are some of the requirements or the step-by-step process which they are going to perform, and the first step being performing a draft analysis, right? Now coming to some of the complex factors is basically the undercuts. So there will be some additional parts available for a plastic component which cannot be actually ejected along the main tooling direction. Okay, so if you could see the ejection or the main tooling direction is vertical, and then you can see another additional part available for this particular red plastic component. Okay, so if this is the case, you have the core block and then the cavity block accordingly. Now in this case it will be difficult for the ejection. Okay, ideal case it has to be ejected perpendicular to the normal tooling direction, or we need to have some mechanisms made available for making sure that that actually works out. Okay, so undercut is basically an indentation or protrusion that prohibits the ejection of the molded part along the main tooling direction what you are having along the tooling direction which we have created for the core and cavity. Okay, so we'll try to understand how we can avoid this. Okay, now basically whenever you are provided with a class A surface, uh, the given surface what you can actually see with our naked eyes, which has the aesthetic look, is basically your class A surface. Okay, So basically the surface behind it with respect to the thickness what we are going to provide is generally going to be a B surface. So general case plastic components will be having a thickness. So there is a standard parameter with respect to what is the thickness which you are going to provide it to your plastic components also. Okay. So plastic components are going to have a thickness of around 2.5 to 3 mm. Okay, so that is going to be the general thickness which we generally provide for plastic components. Okay, so the figure you here see here on the top is basically showcasing the class A surface of a B pillar component. A B pillar component is where you are going to have your seat belt mountings. Okay, so that's what you can see in the figure on top, and in the same image, the bottom part of the B pillar area, and then the non-appearing side, or what we generally don't see, where the joining elements are being provided or joining features are being provided for the plastic component is showcased in the figure below. Okay, so this is how the backside or the B surface of your plastic component will look like finally. It will be having some of these features. These rectangular and square patterns are basically ribs. We are going to deal with what are ribs also. And then we have some features like the dog houses as well as the blue part called as a pushpin. Okay, we are going to understand what are these components and then what are the usage with respect to plastic component development. Okay, so we are going to deal with in the upcoming slides, right? So this is an actual model. Okay, I have taken some pictures with respect to an actual model. We could see here. So this basically the image shows the class A surface, and then you can actually see the backside, basically your plastic B-side features. Actually, okay, you can see you can see some of the marks. Basically, these are some of the ejector pin marks. Okay, and then you can see the ribs, which are basically to provide strength, and then we can see some push pins and etc. For it to be have a temporary join with respect to the sheet metal parts. Okay, we'll try to understand about these things. So some of the engineering features which we generally see in a plastic are ribs, screw bosses, locators, heat stakes, and dog houses. Okay, so let's try to understand one by one. So ribs are created on a non-appearing surface of the plastic part. So ribs are provided to increase strength of the component. Okay, so ribs are basically designed for providing strength. Okay, the structure some looks something like this. Okay, wherever there is a strength parameter required, we are actually going to provide the ribs. It can be of different shapes. It can be a normal rectangular shape. Sometimes it can be a honeycomb like structure. Some of the areas where you can find honeycomb like structure is basically a speaker grill area. Okay, and in general other areas you can find this kind of simple rib. Okay, in the previous image also we just saw a rectangular rib like structure which are actually providing strength. These components are very long, okay, compared to the other plastics. Okay, so these are pillar components, okay, in your car. Okay, so these are going to be requiring much strength so that it doesn't flux easily. Okay, hence we are actually going to provide these kind of rib like structures or rib structures. Okay, now some other design considerations for ribs are basically its thickness parameter, the draft, the rib root thickness, height, as well as the spacings what you are going to provide with respect to whenever they are having multiple ribs. Okay, so basically these are some of the nomenclatures, okay, we are having. So you can see some of the parameters basically here. Okay, so the bottom wall thickness T is basically the plastic thickness with respect to the value which we generally provide for plastic. Basically is going to be in the range of 2.5 to 3 mm. Okay, so basically that's what is going to be your wall thickness. Okay, now basically you are having a rib like structure or a rib structure available here which is having a rib depth. Okay, so it's actually in the range of less than or equal to 5t. Okay, the rib height is going to be in the range of less than or equal to 5t. Okay, so that is going to be the parameter with respect to the rib depth. Along with that, you will be having the rib draft angle. Okay, the draft angle is already a set parameter. It can have draft uh, as less as 0.5 degree to 2 degree. Okay, so as the uh, draft increases, the depth also has a parameter accordingly changed. Okay, now another parameter with respect to your rib component design is basically a rib root thickness. Okay, so this is one of the major parameter which we need to focus while we are designing the components, because if you don't have this rib root thickness meeting our condition, then there are chances that you can have plastic defects develop. Okay, there is a fillet radius which we generally provided for the rib what we are creating, which can be a minimum of 0.25 mm. Okay, so that will be the radius which we generally give. Now rib root thickness should not be actually more than uh, whenever you are having the thickness of the wall as 2.5, so ideal case it should not be not more than 1.25 times the wall thickness, so it will be around 3.25. Okay, so the rib root thickness should not be more than that. Okay, so we need to make sure that that is being taken care of whenever you are actually looking into developing these rib thickness. If the rib thickness uh, is going to be more, then it can lead to plastic defects. Okay, we'll try to understand what are the defects also moving forward. So the next component with respect to engineering features is basically the screw bosses. Screw bosses are used for attachment and assembly of components. Okay, so basically you can see one part of your plastic component. This, if you could closely watch, this is basically a drill. Okay, a drilling machine part. Okay, so one half of the drilling machine part is here. Sorry, we have another side which is available for this particular drilling machine also. Okay, so now those two components will be joined together, and then it will be fastened together with these screw bosses, and you are going to have the screws bolted here. Okay, or screws being tightened here. Okay, so these bosses will be having the self tapping screws available for having the arrangement according. Okay, or it can be already having threads available. Okay, so these kind of cylindrical projections with holes to fasten the screws and threaded inserts are generally called as screw bosses. Okay, so just like any other engineering feature, for screw boss also we are going to have some engineering features. Okay, or design features. Okay, so basically when you see your screw, okay, it will be the screw can have a head area which will be much more having the diameter of the head will be much more than the diameter of your body of your screw. So you can see the body of the screw will be having a diameter of small d, and then capital D as such will be actually available, which should be maintained accordingly to make sure that you are actually having your screw boss provided with the proper conditions. Okay, so whenever you mention these things, you should also follow the draft condition also. Okay, similar like your rim, you should be having minimum of 0.5 degree draft. Okay, and the fillet radius are also available on the inside as well as outside. Okay? So if you see the outside, the draft direction, and then the draft available inside the screw boss also having a different direction. Okay, you can see the draft outside is stooping inwards, and then on the inside is stooping outwards. Okay, so these are some of the requirements you are having. Okay, whenever you are actually creating your mold, these are some of the considerations also which you are going to have with respect to your mold development. Okay, so these are some of the conditions which you need to follow, and then along with that, the depth of this particular hole should be 0.3 times the thickness factor. Okay, so this depth is required to make sure that the wall thickness is not more. Okay, right guys, so these are some of the parameters we need to look into while we design the screw bosses. Okay, make sure that you have a good idea about understanding. If you are able to give a better idea of one of the uh, design rule, basically you can actually relate accordingly what are the other parameters. Okay, so make sure that you are able to look into all those parameters, and design calculations are done whenever you are designing any engineering feature for your plastic components what we develop. Okay, so these are very important as a design engineer to follow. Now coming to the next part is basically plastic staking, or we generally call it as heat staking or thermal staking. Okay, so this is basically a permanent joining operation which we perform for plastic components. Basically, we are actually joining one plastic component with another plastic. Okay, so what happens is basically you will be having a screw boss like structure. You will be having a structure available. We are going to have something called as a plastic staking tool, okay, or heat staking tool, which is actually going to apply heat to this particular staking available heat stake available on your plastic component, and then it is actually going to melt, and then actually it is actually going to form a shape for this particular melted plastic so that it actually joins the two plastic components together. Okay, so it's going to be a permanent joining operation with respect to plastic components, wherein those two plastic components will be joined finally. Okay, we'll be actually seeing an actual example of heat staking moving forward, but these are generally done with respect to assembled plastic components in your car structure. Okay, for example, you are having a door panel and there are multiple plastic components. We actually do a permanent join for these plastic components, and now you'll be having a question with respect to how we are actually going to replace those components, or how we actually can perform different operations. Right, so now since plastic components are easily manufacturable, we can always go for the option of replacing the whole part very easily, or since it's a permanent joint, we might have to apply the heat. We'll have to reheat it so that it can be removed, and then we can apply a new part over there. Okay, so replacing is going to be a better option here for plastic completely. Okay, the door panel can be completely changed and then a new panel can be provided. So hence we can find this kind of temporary joints also available in plastic components. Right. So for heat staking also we have general design criteria. So the inner diameter of 5 mm, minimum 5 mm, and the outer diameter of 7 mm, basically constituting a wall thickness of 1 mm will be there with respect to the plastic, and then the plastic with the stud or the heat stake, and then the other plastic where it is going to be joined. You will be having a hole through which the plastic heat stake comes up. So with respect to that wall to wall, we'll be having a clearance of minimum of 0.5, okay, for a maximum value of 0.5. Okay, and then the length of the heat stake which comes out of the other plastic component should be minimum of 12 mm, so that we can actually perform the staking operation. Okay, so when the plastic melts, it is actually going to cover the top surface of this particular yellow part, and then it fixes both components together. Okay, hence these two criteria with respect to the depth, the height, etc., should be maintained. Okay, so these are some of the criteria which you need to follow. Right, even you will be having ribs for your heat staking part. Okay, based on the conditions it will vary. Okay, but some of the conditions which we see here are very critical with respect to heat staking operation. Right, now with respect to heat staking, there are different types of heat staking tool available, and then some of the cross sectional areas also changes accordingly. Okay, so heat staking, some of the materials, plastic materials which we generally see are polycarbonate, polystyrene, polypropylene, ABS, and nylon material. Okay, these are some of the plastic materials used for developing automotive plastic components as such. And then the heat staking tool which performs the heat staking operation can be of different shapes. It can be a flat shape, it can be of a dimple shape, or it forms a dimple after the heat staking operation is performed. It can be a cross shape or it can be a rosette shape. Okay, so you can see how the finalized product will look like in the last row. Okay, so in the last row you can see how the finalized product will look like. There can be a hollow heat stick as well as solid heat stick. Based on the area of usage it varies, or based on the manufacturer it varies accordingly. Right, so that being said, this is basically how the heat staking will look like. Okay, so you can see the last operation of heat stake. The rosette type of heat stake is what you can see here. Okay, so it's a finalized product. You'll see this is going to be a aesthetic part available on your door side door panel, and you can see how it is being actually joined with other plastic components. You can see the color variations also, wherein you understand the different plastics accordingly. So now coming to the next, one of the major engineering feature is going to be your doghouse. So doghouse is going to be a supporting feature for your plastic trims. Okay, so these are used for attachment. These are also made sure for adding the required height for the components like screw bosses, locators, etc. As well as it also is used when you are having a tooling direction perpendicular to the main tooling direction. Okay, so for those requirements, you can have the use of doghouse. Okay, doghouse has its own design criteria. Basically, the height of this component, the draft angle, it should be minimum of 0.5 degree to 3 degree accordingly. And you can see there is a small clearance is required on the bottom, which is given by the letter C. Okay, so that should be 40% of the wall thickness. Okay, why that is being provided is basically to avoid any plastic defects. So whenever the molten material enters to this area to take the shape of this particular doghouse, then there is more chances that all the material goes to that area, and then on the top side or the class A side there is going to be a void area being generated. Okay, to make sure that that is avoided, we are actually going to neck or reduce the uh, thickness at that particular area. Okay, so that way the amount of molten material flowing to that area is reduced, or the pressure and then the speed at which the molten material goes to it reduced, so that there is uniform flow on the horizontal direction as well. Okay, so these are some of the things which you need to look into with respect to developing your doghouse. So we'll try to see some of the doghouse also, and then the height of this structure, the B height, what we generally see is going to be 3 to 6 mm. Okay, general criteria 3 to 6 mm, so that we can actually maintain this structure. Okay, so this is actually a doghouse which you can see in an actual plastic component. So you can see how the conditions are applied for the B, the thickness at the root, the root, the root thickness here of the doghouse. You can also actually see for strength purpose it has been provided with another extra rib, as well as there is a cutting on the top. Okay, so the cutting is to facilitate and another engineering feature for a temporary joining operation. Okay, so we'll try to see the image with those components also. So here you can see the doghouse with a push pin or a push clip. Okay, so these are components which are used for temporary joint with respect to your plastic components. Okay, so this will be the part which will be used for assembling the whole plastic assembly component of your door panel, for example, to be joined with the sheet metal part of your car. Okay. So why there is a temporary joint required is basically you need to perform operations. So if you see your plastic door panel or your door panel, you can see lots of wiring systems available. Okay, for example, you'll be having the window winding motor, you will be having the stereo system, you will be having the other switches, etc. Okay, so hence we are actually going to make sure that we are actually going to join this particular uh, plastic component or the assembly of the plastic component with the sheet metal part using temporary joints, and hence we are going to find the use of push clips. Okay, this is actually going to make sure that the proper fixing is available with respect to the sheet metal part, but when there is a requirement for serviceability, we can actually remove it. Okay, these are the simple plastic components, and then if there is any damage to this part, we can actually replace it also. Correct. So that is the use of push pin, push clip, and then the doghouse arrangement here. Now let's try to see some of the other plastic components. Okay, so it's the locator. So let's try to look into more about locators in plastics. Okay, so as the name suggests, it's basically used for locating the part with respect to the other components. Okay, so when you look into the locating parameter, we try to look into some of the GD&T parameters also, the geometric dimensioning and tolerancing. So what that is basically with respect to arresting the degrees of freedom with respect to motion of the plastic components. Okay, So it's used for locating, as the name suggests, locator. What you see here is a four-way locator. So there are two types of locators which we generally see in the automotives plastic components. One is the two-way locator, and then one is the four-way locator. So the combination of two-way locators and four-way locators generally will be utilized for you to actually make sure that it's located with respect to the sheet metal part, and it also arrests the motion of a particular component. Okay, so that is what we generally do with respect to locators. And then finally, you will be having the other operations performed, like your push pins, etc., provided accordingly for the final assembly with respect to your sheet metal parts. Okay, so hence these kind of components are being used. Okay, sometimes we might not find much of locators in your plastic components, and then these screw bolts and other things are actually going to perform the function of a locator. Okay, so these are some of the things which we need to look into while we have an understanding about plastics and the plastic features. This another image where four-way locator. Hope you can see it properly. Now this image actually clearly showcases a side door panel which has all the major engineering features involved in here. Okay, on the top sandal color part or the white part, you can actually see some of the heat taking operations being performed, and then also the ribs. Okay? The ribs can be seen on that particular white part. Below again, you can see your doghouse on the top right corner, and then further on the other sides, you can actually see the heat stakes. Okay, on the bottom part again, you can see doghouses which are actually located along with the wall structure. And then on the speaker grill again, you can see some honeycomb rib structures. On the other areas where which are longer components, again you can see rib structures available. Okay, on the other sides, you can also on the top of the component also you can see some push pins as well as other components actually available for joining operations to be performed. Okay, so this is how the B side of a plastic assembled part will look like finally for a door panel. Okay, so some of the features are used for permanent joints, and then the features with the push pins allow for temporary joints. So you can see around the periphery of your door panel, basically it's doghouse and push pins. So that is to make sure that we can easily uh, provide the required tools for removing the plastic door component for serviceability and servicing work. Okay, so this is how a complete plastic component is going to look like, and then as a design engineer, you'll be working on designing components like this. Okay, now let's try to deal with some of the injection molding defects. So you can see the major or some of the major defects you can see with respect to injection molded plastic components are sink marks. So as we were discussing, these sink marks are basically caused because of the improper design or improper design of your wall thickness with respect to your rib and other components. Okay, so if the rib root thickness condition is not maintained, then there are chances that you will be having a hollow portion or a sink mark available on the class A surface, which can be a serious concern with respect to aesthetic surface development. Okay, so we need to make sure that we actually have a correct design with respect to your rib root thickness, and then we are actually providing the required fillet so that there is smooth flow available for the molten plastic material to go through. Okay, so this is one condition or one plastic defect and how we can resolve it. Second is basically the shrinkage. Shrinkage is the volumetric contraction of your plastic during the cooling. Okay, so as you can see, just like metal parts which expands and contracts, same happens for your plastic to an extent. Okay, so polymer composition, material properties, and processing condition accounts for shrinkage. Okay, the composition of the polymer, etc., deals to shrinkage, or general case there will be shrinkage. So how we can actually avoid this is basically by giving some shrinkage allowances. So whenever we are actually designing the core or the mold parts, the designer actually gives something called a shrinkage allowance a tolerance value which actually looks into this shrinkage condition, so that the final product will have the exact design. Okay, so that extra uh, uh, condition will be provided, or extra millimeters will be provided, so that the molded material can shrink to the required size finally. Okay, so that is the shrinkage condition and the shrinkage elements which we generally give us to avoid shrinkages. Warpage is basically the distortion of the intended shape of the molten part during cooling process. So as the part cools down because of the length of the component, or because of the non-uniform thicknesses of the parts, there can be distortion in the shape finally when it cools down, or the intended shape is not met finally when it cools down. Okay, so this can be avoided by making sure that there is no sudden changes in the thicknesses, and then there is a gradual change in the thickness actually provided, and then wherever there is a requirement for engineering features like grips and other things provided is being provided to avoid these warpages. Now coming to the drag marks, this is basically happening because you didn't design the mold components properly, or the amount of draft you provided is not sufficient, or there was a zero draft provided to the mold. What happens generally is basically it scraps the plastic component, and then the aesthetic looks of the part is being destroyed. Okay, so you get actually a very rough surface. Okay, so that's what we generally see. So this is what we generally can see with respect to your plastic components. Some marks, drag marks will be available on the plastic because of the improper draft angle creation. Okay, so this can be avoided by making sure that the proper draft is being set for the mold components, right? The another plastic defects we generally see is called as short. So basically this is because of the inadequate filling of material, resulting in the incomplete part being manufactured. Okay, so there can be reasons like the injection pressure was not enough. There can be air entrapment inside the mold cavity when it's close together, which doesn't allow for the plastic to settle down into that particular area. Okay, so to avoid this, there can be air vents available on your mold. Okay, we can actually provide some air vents available on your mold part. Sometimes what you generally see is you will be having your ejector pins. There is some clearances provided to the ejector pins so that this air can escape through those small tiny holes available uh, along this ejector pin area. Okay, so these are some of the things we generally provide to make sure that short is avoided. Okay, coming to the next part is flash. Flash is a major concern with respect to excessive material forming during molding in the parting surface area. Okay, so the plastic material moves out from the area where the core and cavity actually meets. Okay, so this is basically because the molds are not closed properly, or because of the improper mold alignment, or the injection pressure is more than the clamping pressure. Okay, so since the clamping pressure is not enough compared to the injection pressure, this pressure makes the plastic to eject out to the small gaps available in the parting surface. Okay, and then we'll have an extra material available, generally called as a flash. So what we need to do is we need to perform an additional operation to trim off these additional surfaces. Okay, so this is what we call it as flash. How we can avoid is to make sure that proper clamping is done, proper alignment is there for the core blocks, core and cavity blocks, and then also making sure that injection pressure is adequate, right? So these are the things which we can do to make sure that the flash can be avoided in, as defect in plastics, right? Now another thing is basically jetting. If you could see the image, you can see some additional jet lines kind of thing, or lines, irregular patterns available on the plastic component. This can be due to the velocity, the high velocity of at which the molten material is injected, and then maybe it can be because of the improper designing of the gates and runners. Okay. So we can actually make sure that the injection pressure is enough, adequate, and then you are having the nozzle size proper. Okay. So these can actually make sure the jetting can be avoided. So these are some of the plastic defects which we actually see here with respect to injection molding plastic operation. So we need to make sure that we have proper design criteria followed, as well as proper checks being done with respect to your manufacturing operations to make sure that injection molding defects can be avoided, right? Now coming to some of the standard plastic design practices. So wall thickness, we need to make sure that wall thickness strongly influences the moldability of the part, and hence we need to make sure that the uniform wall thicknesses are maintained. Okay. If the wall thickness is higher, then it can lead to plastic defects. And then with respect to all the engineering features also, these wall thickness should be designed properly so that wherever there is a requirement for strength and then joining operations to perform, it is able to do that. Okay, it's able to perform its operation basically, right? Now there should not be any sudden change, and there should be a smooth transition possible so that the plastic material can flow easily, and then hence we need to have something which you can see in the second design here. So smooth transition is very important. Okay, so instead of having a very sharp corner, we try to apply some fillets so that we have a very smooth design. Same thing goes for the adjacent corners. There should not be any sharp corners available in plastic parts. This can actually increase the stress and damage the part. Okay, so make sure that there are fillets being applied on the corners, and then this is also maintained by having a proper thickness. So basically, if you could see, the internal radius is going to be 5 mm, for example, and you are having a thickness of 2 mm, then we need to make sure that the calculation is done accordingly with respect to the internal radius as well as the thickness, so that you have, for example, you are having internal radius as 5 and the thickness as 2, then the external radius will be 5 plus the thickness, the internal radius plus the thickness value. Okay, so this is how you need to calculate it so that you can have uniform thickness maintained, so that it actually leads to proper flow of injection molded material. Now coming to the core or core out, this is basically some of the standard practices which you need to follow to make sure that there is no warpage or sink marks. Okay, this happens because uh, the plastic molten material tends to go to that particular area instead of flowing into other areas. Okay, so this can actually lead to sink marks to develop. So we are going to optimize the design, or coring out is being done to make sure that there is proper mold flow around the system. Okay, and then cooling time can be reduced. If there is a proper design like what you can see on the second image here is provided, then the cooling time can be reduced, and then you will have a proper design developed. Right? It can be with respect to your screw boss and other things. It can be with respect to your snap fit and other components also, as well as the general design criteria. Right? So now let's try to see into core out with respect to other components. You can see an incorrect design with respect to a kind of a bush kind of material. So you can see how the design has been corrected by hollowing out material so that they have a rib kind of design, so that it doesn't lead to sink marks and other plastic defects, or cooling anomalies can be avoided. Right? This is how the design will look like finally. So you can see the incorrect design coring, and then the correct design how the coring is performed. Correct. So this is how the wall thickness are maintained, and then you will be having a proper design. Right. Now coming to the bosses, so this is basically the screw bosses. You can see the incorrect image. So it looks fine, but what happens here is basically the wall thickness varies. Okay, sudden changes in wall thickness appears, and then this can again lead to problem. So you can see the correct design how they have maintained it, so that the core out is being done again for the boss areas and all, so that you have ribs and then core out done, so that you have a better design. Okay, so this is what is going to be performed accordingly to make sure that you are having a better design. Right. So now let's try to understand some of the advantages and disadvantages with respect to plastics. I'll check in with respect to general criteria of plastics so that we also understand what are the things which we need to look into. Okay, so Plastic being a versatile material which forms an integral part of our life, daily life, and having been catered to almost all the industry. Okay, so if you talk about any industry, we generally deal with plastics. In our household, most of the components can be made out of plastics as well. Okay, it has its own advantages and shortcomings. Okay, so let's try to see some of the advantages. It's a very extremely versatile material, and it has the ability to tailor made in different shapes based on different operations. Okay, based on the different uh, requirement what we are having. Okay, so wide variety of plastic materials are available, which can be used for different requirements, and then there are wide varieties of properties available like high temperature, uh, susceptibility, um, susceptibility to chemicals and other things. Okay, and then better strength, yeah, transparency. Okay, so that it can be used for different areas, right? So these plastic materials are lightweight in competing with respect to competing materials like metals, and which leads to ease of handling and have an improved efficiency. So when you basically see bumper materials made out of sheet metal, the weight increases, and then you will not having a better efficiency with respect to mileage and other things. So when we reduce the weight of the vehicle comparatively, we can actually increase the mileage of the vehicle. Okay, so hence lightweightness is another one of the advantage of using plastics. Resistance to chemicals and different environment conditions. Very good aesthetics and applied and can be available in different textures and colors. Okay, so that is another parameter. Excellent thermal and electrical insulation is another property. Ease of manufacturing and easily replaceable, and the cost involved in is less compared to other materials. So manufacturing cost involved is comparatively less, and then the replaceability is one another factor considers an advantage for plastics. Okay, so this general is a general requirement or a general advantage with respect to plastics. Now coming to disadvantages, one major issue is with respect to its recyclability. Okay, so it doesn't decompose. Okay, so that stays in the soil for a long time as long as we are there. Okay, so that is one problem with respect to recyclability. Uh, one-time use of plastics, one-time use plastics are hazardous to the environment and can endanger life forms. So that is one problem with respect to plastics. Toxic fumes produced by burning the plastics can be harmful and can lead to cancer and other critical conditions in human beings as well as in animals. Right. Manufacturing of plastic itself is a process where chemicals are involved which are hazardous to the environment. Correct. So whenever you are actually manufacturing, there are additives and other things added which are actually very harmful to the environment. Correct. So these are some of the cons, pros and cons which we have with respect to plastics. But coming to a conclusion, basically plastics are inevitable part of our life. As engineers, our part would be to find ways to use it properly, recycle it effectively, and find new technologies to make sure how contamination due to plastic waste can be reduced. Correct. So that is should be our goal. As a design engineer, we should try to evolve technologies to optimize the design and to reduce the scrap and inculcate best manufacturing practices to develop plastic components. Correct. So these are some of the things as a design engineer which we need to follow. This is what you are going to do also, right? So having said that, I will just conclude my session here.